So my talk is about an idea to illustrate some properties of geometric algebra, which only shows up in 5 dimensions. And thinking about things even in 4 dimensions is possible, a little bit hard, but thinking in 5 dimensions is even more challenging. But if you do it in a color space instead of a spatial dimensions, it becomes actually intuitive and more easy to remember and seeing some properties which otherwise is difficult. So it's just an idea which is supposed to be a little bit of an inspiration to see what else it can be used for. So I'll start to do it by a little bit making a review of the concept of what a vector is in the field of differential geometry, which is my original background, and later I came to geometric algebra. We had different kinds of concepts of vectors which we encounter there, like vectors, covectors in differential geometry, and geometric algebra has the concept of bivectors and antivectors. And I always want to have a visual representation of everything to see what it means visually, what it is. So I'm coming up with some visual representations of all these concepts. Coming to the main question, what is the relationship between the covector concept from differential geometry and the bivector concept from geometric algebra? And it's in 3D and 3D space, you basically identify all with everything. In 3D, everything is the same, it's just a vector. But if you go to higher dimensions, we can see that there are certain equivalences which no longer work if you go even to 5D. In the 5D, these become really different objects which are no longer identifiable, so you can really see the difference what they are. It's mostly a little bit of a theoretical thing, a fun part, but I'm discussing maybe 2 ideas where it might have possible applications. And maybe main purpose of the talk is to maybe give some inspirations on how we can think in color space to visualize something in high dimensions rather than choosing spatial dimensions for these properties. So first, a little bit review of the structure of multivectors. Basically, the Grassmann algebra in arbitrary dimensions. In 2D, a multivector has 4 components. There's 1 scalar, 2 vectors, 1 bivector. It makes a 2D multivector. In 3D, the components are a scalar. We have 3 directions. We have 3 bivectors, 2 planes, 3 planes in 1 volume element. It's an 8-dimensional objects. And if you play this game to the higher dimensions, it's this Pascal triangle. We have just adding the objects in a binomial form. Like in 3D, we have 3 vectors, 3 bivectors. In 4D, we have 4 vectors, 6 bivectors, 4 volume elements, 1 hypervolume. In 5D, we come to the 5, 10, 10, 5, 1 structure of a multivector. The blades, the vectors, are like the left-directed first step, the first linear plane, so to say. It's always 1-dimensional objects. The bivectors are 1 step below. The 3-dimensional elements with 3 vectors or even 1 step further. This is where the vectors, bivectors live. And we're having the concept of the antivectors in geometric algebra, which is basically just a complement from a vector to what it complements to get to the full space volume to the antiscalar. And a bivector in 3D is an antivector of a vector. And the antivectors are like the blades in this triangle coming from the right side. The 1-dimensional object, 2-dimensional objects, 3-dimensional objects coming from the right to the left. The antivectors, this is where we reside. Geometric calculus is the interesting part of how to unite differential geometry. It's a very important mathematical field with geometric algebra. I'm not going into the calculus part, only discussing the structures of the basic elements with what we are dealing with. So in differential geometry, having the concept of a tangential vector as a derivative along a curve. We have a function, it maps from a manifold to a real space, a different curve. The change of the points along the curve, this is what defines a tangential vector in differential geometry. It can be written in coordinates. We don't want to use heat coordinates, but everything can be represented in coordinates. And when written, the tangential vector in coordinates is a linear combination of the basis elements, and the basis vectors are the derivatives by the coordinate directions. These are the basis vectors in the derivatives. And there's the concept of a manifold, which is not a vector space, it's just an arbitrary topological space with certain properties, not necessarily vector space, but a tangential space where we can compute derivatives, which is always a vector space. At each point is a different vector space, but here we have the derivatives, and the derivatives are defined by the coordinate space. And here, using these coordinate directions, we can build the Grassmann algebra in the tangential space, like we're making the wedge product of basis functions of directions in each field. So we're having a covector, no, not a covector, it's a bivector of the tangential vectors. Then differential geometry also defines the concept of a covector. A covector is a map of a vector to a number. So it's basically a dual. It is defined by applying a function to a vector. This function is then the covector. It also, like the derivative, fulfills the vector space axioms. We can also write it as a linear combination at a basis, which is then known as a total differential. And the set of these covectors defines the so-called cotangential space, also on each point in the manifold. And this is a natural duality relationship to the tangential vectors, having the covectors, which are dual to each other. And they have different properties. So due to these duality relationships, we can, for instance, consider what happens if you do a coordinate transformation. They always need to be orthogonal, like squeezing the coordinates in one direction. The tangential vectors is the difference between 2 points. What is orthogonal to it? If we do a coordinate transformation, it still needs to be orthogonal. We can immediately see that the covector has a different coordinate transformation under change of coordinates. The vector is always the difference between 2 points. The covector is whatever is orthogonal to this change of 2 points. So it has different properties already on this part. And we can visualize it by thinking like if you have a vector field as little planes. The vectors are local directions, and the covectors is everything which is locally orthogonal to the vectors. Like in 3D, what's orthogonal to a direction is a little plane. Like we have the z direction, we have little planes in the xy direction. We can play with also with your polar basis vectors, like the radial vector is all radial outgoing vectors. This would be the dr vector field, and the dr, the covector field, is the little planes which are always orthogonally oriented here. You can also do it with the azimuthal vector field, which goes around the phi direction. We have the directions and little planes which are orthogonal to it is like a d phi, the covector basis field. In 3D, we can also do using the theta, which is a little more difficult to imagine how it works. But if you make a slice in the 3D field along the polar axis, the theta direction goes from the north pole to the south pole, symmetrically around the axis. This defines like the tangential vector field, the d theta, partial theta, and orthogonal to it, the covector field is like little cones around the polar axis, the z-axis. It's one way to visualize the covector field of the basis vectors in the radial basis functions. And all these vectors are always orthogonal. The covectors are orthogonal to each other, and also the vector fields on each other also orthogonal to each other. And the partials and the d's are also orthogonal to each other. You can play it in different coordinates, and as long as the coordinates are orthogonal, these properties will always be the same. Just an idea how to visualize them. And in general, covector is like a local advancement of a function. So like the total differential of a function, you can think of it like something similar to an isosurface, an isosvolume or equipotential surface. We have an advancement of a scalar function like a gradient here. When the covector along a line here of this function would be the little gradients along the plane here. So covector is basically imaginable is a little plane, but a bivector in geometric algebra is also a little bit plane. And if you come from a direction, you can think what is actually the difference between the dz and the bi-tangential vector, which is also a plane. Is it the same object, or is it they looking the same? And this is like the question that was wondering about: how is it similar? How is it not similar? Again, let's go to the structure of the Grassmann algebra, the Pascal triangle, and the space is similar, like the tangential vectors like that are lying in this plane, and the covectors like same as the antivectors lying with our plane. So in 2D is, of course, we are just identical. We have the same number of components in all dimensions. And so in Euclidean algebra, you just identify them with each other. In 2D, we are exactly the same. In 3D, we are not the same, but they have the same number of components. This is sometimes a confusion between vectors and axial vectors and polar vectors, but they have the same dimensions. So people tend to identify them, even though they are different objects. If we go to the bivectors, is one step further. There's still some overlap. Like in 4D, we're having 6 bivectors. And of course, 6 bivectors is certainly different from having 4 bivectors. So here in 4 dimensions, it's already different between the vector and the bivector. They can't be the same objects. We have a different number of components. But there's still some overlap that the covectors and the Bi-Covectors are still in the same point here, overlapping here. So here we still have equivalences, and only in 5D, all these objects are actually becoming unique. So we can actually see that they're really different objects, different properties, which only in lower dimensions tend to be identified, which can cause confusion, of course, because the same object has different properties. Before telling it, you wouldn't know. In 5D, it becomes really unique. So my question to myself and to my colleagues was, how can we actually see that intuitively? What happens here? How do it in 5D? Now the idea is to do it on the color space instead of just spatial dimensions. Spatial, it becomes a little bit confusing at some point. So the idea is we identify the tangential vectors, the basis dimensions with light. Like the x direction, we use red light. The y direction, we use green light. The z direction, we use blue light. These are our basis vectors, and we can define the covector, the bivectors as a combination of red and green becomes yellow, like a plane. Green and blue becomes cyan. Blue and red becomes magenta. And we have one volume element, which is all colors combined, which is white. So this is like the basis vectors in the 3-dimensional color space by adding light. And we can also represent the co-tangential Grassmann algebra by starting from the covectors, which is coming from the other side. This means here the basis vectors, the dx is like a plane element of cyan. It's like a filter which is reducing colors instead of adding colors. So we're starting with a cyan filter, a magenta filter, and a yellow filter. And if we combine them, if we do the outer product between a cyan filter and a magenta filter, we're getting a blue line, so to say. Magenta filtered with yellow becomes red. And yellow filtered with cyan becomes green. And if you combine it all together, becoming like an anti-light volume, which is the black element. So this is a way to have 2 algebras of the colors in 3D. And the 3D RGB multivector of a tangential space is like a linear combination, like black plus 3 fundamental colors, additive colors, plus 3 combined colors, plus a white element. With an additive color scheme, it corresponds to a light emission. And if we come from the other side, we are in the cyan, magenta, yellow color space of a subtractive color scheme, like light filters, starting with like a white scalar, cyan, magenta, yellow, putting them all together. So like a multivector in the subtractive color scheme. And here, of course, we can actually see the equivalences as well. But in 3D, the covector is the same as a bivector, and the Bi-Covector is the same as a tangential vectors. Just if you look at the elements here, for instance, the bivector, which is blue, outer product with red is magenta, as well as the basis vector from our side is magenta, is the same equivalence which we can see here or here. So this is overlap in 3D, which you can directly see in color space. Now, of course, we want to have it one step further to see the difference in the 4-dimensional space. 4 dimensions is maybe known a little bit from the spacetime algebra. We can think about the fourth dimension as just writing a number axis here. With a little bit imagination, it works. If we have 3 possible bivectors, we have 1 spatial and 1 time component, and 3 possible bivectors which are only spatial. So you can see we have 6 bivectors in 4 dimensions. In 4D it kind of works, but we can do it with a color space by adding a 4th dimension transparency, it's a 4th component. Then we can build also 6 bivectors. It's constructed by non-transparent mixed colors. These are 3 possible combinations, and 3 transparent pure colors. So these are our 6 possible bivectors in 4-dimensional RGBA scheme, so to say. So basic structure in 4D, you can also define the 4 antivectors like volumes, which is transparent mixed colors and 1 non-transparent white. And the hypervolume with all 4 properties together is like a transparent white. This was the additive color scheme. And to construct a covector, you would go from the other side, like reducing a property, filtering a property from a full volume, like cutting off an element from a hypervolume. For instance, if you're starting from a full volume, the transparent volume, the transparent white, we're cutting off 1 property, the red, and we're getting transparent cyan. So it's like the recipe how to construct a Bi-Covector in 4D by either combining 2 properties. There are 2 ways to do it. We can combine 2 properties like blue and cyan. It becomes non-transparent cyan. Green and blue becomes non-transparent cyan. Or we reduce 2 properties from a hypervolume. From transparent white, we reduce the transparent and the red property. We're also getting the same bivector, which is the non-transparent cyan. And these are the visual equivalences which we have in 4D. Vectors are not the antivectors. We are, of course, distinct. We have 4 vectors. We have 4 antivectors, which are properties with 4 elements. But the bivectors and the bi-antivectors or bi-covectors, they are visually the same in 4 dimensions. Like we can describe opaque cyan, which is blue and green, also as not transparent and not red. It's equivalent in 4D. This means we are now here, in this plane here. The vectors are distinct from the antivectors, but the bivectors and the bi-covectors, they are visually equivalent in 4D. So what have we learned so far? We have, even though we have the same amount of components, we might have still different meanings, but the identifications which we are used in 3D, like in 3D we identify a vector with a Bi-Covector, it does not transport over the higher dimensions. In 4 dimensions, a bivector is identical to a Bi-Covector. And the uniqueness we only get if you go to the 5 dimensions. What we really want to see what is unique is to be down here. When each of these elements, the vector, the covector, the Bi-Covector should be really unique here and no longer identifiable. And here the idea is to use the texture as a 5th dimension. So we have red, green, blue, basic colors, transparency, and a texture property. This defines 5 dimensions. It defines when 5-dimensional space of color patterns. We're just getting higher dimensional basis plates by adding number of properties. The 0-dimensional object is like a scalar, just black. We have 1 color, we have a vector. A bivector is a color plus pattern property, texture property. If it's transparent, it's a trivector. It has 3 properties. If you're adding another color, it's an antivector. It's a 4-dimensional hypervolume. If it's all together like a transparent white textured volume, it's an antiscalar in 5D. And now we can use the similar recipe to construct what is a bivector, combining 2 properties. And a bivector and a bivector is a bi-covector. And here we can just cutting off 2 properties from a hypervolume. Hypervolume is a 5-dimensional object. If you cut off 2 properties, we're getting a 3-dimensional object, the bi-covector. And now we can kind of add together what are the possible bivectors in 5D, which must be 10 possible bivectors, which are the 3 possible mixed colors, 3 possible pure colors, 3 possible textured pure colors, and 1 white, non-transparent black color. So we have basically 10 possibilities to combine 2 colors, which gives us the space of bivectors. And we can also construct with a set of Bi-Covectors, where 3 vectors in 5D, we have 5 three-dimensional objects, by combining 3 properties. These are when they're mixed, transparent colors, cyan transparent, magenta transparent, and yellow transparent. First 3, or by removing 2 properties from full volume, like a textured cyan, textured magenta, textured yellow. Or we're having a white, non-textured, non-transparent, and we have pure colors, which are transparent and textures. This gives a set of Bi-Covectors coming from the right side. And the last object, the full one, would be the hypervolume, which is white, transparent in colors, which is all the 5 properties. So we have the 5 colors, 5 covectors, which we can construct by combining either 4 properties or removing 1 property from a full volume. And now if we list all the properties, all the possible bivectors together, like the 2-dimensional objects, these are the possible 10 ones which we can do, and the possible Bi-Covectors which have 3 properties, and we have no single visual equivalence anymore. So here in the 5-dimensional space, each of the objects becomes unique. We cannot find anymore any Bi-Covector which is visually equivalent to a bivector. So visually, we now have this kind of uniqueness. They're different. The vectors and antivectors are still both 5-dimensional, but they look different. Vectors look different to bivectors. The covectors look different to the vectors. And basically here, we have to find that the vectors can represent directions. The covectors represent the full space minus 1 directions. The bivectors represent like a plane defined by 2 dimensions, and the Bi-Covector represents 2 directions cut off from a full space. And all these 4 different kind of vectors in 3D were always 3-dimensional objects were identified by each other. You can't really see that they are different, even though they have different properties. In 5D, it becomes unique one. So now little ideas, maybe what can we do with it? I mean, this was just an idea how we can use it for illustration, 5-dimensional space instead of using spatial dimensions, using colors, doing some combination. What sometimes is used with a color algebra is to identify the RGB with quaternions. We had a talk this morning. We have a scalar and a bivector, and then do Clifford transformations for image processing. But here we're going a little bit further and using just RGB plus transparency, or RGB and the texture property as a basis vectors. And the multivectors are then combinations of colors and texture combinations. One possible idea might be something like a perception theory of color patterns. And there was an interesting paper coming from Vision Research asking the question, if you see similar images, like pattern images, simple elements, how does the human mind identify or perceive which patterns are similar to each other? And they interestingly found a 5-dimensional parameter space, like 5 properties defining what we see first, and also 5 similarity rules defining which kind of patterns images look similar, which is not necessarily the same. Like before, I was basically just talking about the Grassmann algebra in the color space, but this perception theory might actually define a metric and similarity rules, which bivectors or vectors have which distance from each other. For instance, if you're looking at these 4 images, you can ask the question, which images look most similar? The first, which you see, of course, is these are green and these are red. This is the first impression which you get. But if you ask what is actually similar, you might go, these images are similar because they have the same structure, like the same pattern here. We show the same objects. So the first which you see is the color, but the similarity is more based on the structure. And in this article, we found this perceptual color space, The most visual prominent property we found was the overall color, then the direction and orientation of the patterns, then the regularity of the placement rules, then the purity of the colors, and the weakest property, the pattern complexity and how heavy the pattern is. This is what you see. If you have a single pattern, what is most prominent to you, what is most impressive, kind of. But if you ask which patterns look mostly similar, then it's actually the rule of equal pattern comes first. Like you're looking for the structure. If the structure is the same, then experience the image is mostly similar, not so much of the overall color. Overall experience, similar pattern, dominant color, and so on. We found 5 rules based on these 5 dimensions, defining how to perceive pattern similar. So this is not worked out as part of a geometric algebra, but it might be an idea to use rules like that to define a metric, like a binom quadratic form, defining the distance on this column multivectors to do something with it. Another possible application, which was talking with Dietmar about, is what we do in actually a small team, which I'm now working with, which is called urban height mapping. Just a little bit explain what we are doing in my little team, just for work. It's urban height mapping means we're having an airplane. It shoots laser beams down to the surface and scans the surface to get a 3-dimensional object. This is known as LiDAR, data acquisition, and it's combined with aerial photography. We also make an image, a photo, and when you get 2 kind of data sets describing the point distribution or of the surface, the landscape down there, we have an aerial image, and we're having a 3D point cloud. And one question is, how can we use the aerial image to directly put colors in the point cloud? There are different approaches on it. Standard approach is to make it pretty complicated, but the idea would be rather simple: to select one image from observation sequence, to construct an image from a point cloud for the same flight trajectory, which is known, to overlay it. But the problem is that the overlay is not perfectly known. We don't know the exact projection parameters. So if you just project a point cloud with a given parameters and the image, it does not exactly match. It's somehow different. And ideally, we would need to combine or correct the parameters with a perfect projection. And then if this image here was done just manually to adjust the parameters, and then we see that the structures are actually matching. Question is now, and this might be an open question to discussion, how can we do it kind of automatically, how to compare 2 images which have the same structure but not the same colorization, because the image from a LiDAR measurement, like here, it has similar structures like an RGB image, but the colors are totally different. So that is one of the interesting questions. How can we combine that? There are algorithms from computer vision which are doing it. We're trying to explore it. We just started with this project to do this. We have to see if the ideas from computer visions work, but maybe we can do better by using something like a color geometric algebra in higher dimensions and using a pattern space to combine it, and using maybe some point cloud in 5-dimensional color space to map these images to each other. So open for ideas, it's work in progress, and so far, good idea.